Welcome to Maths with EJD. I'm talking about numerical integration again. In the last two videos, we talked about that some part of this already. Talking about numerical integration, we've seen trapezoidal rule, and then we saw a better method than trapezoidal, which is Simpson's rule. Okay. And things can even get better with what is called adaptive quadrature. Interestingly, it's not like adaptive quadrature is a rule of its own or something, but it helps to improve any of the other two rules. So already we had seen trapezoidal rule, we had seen Simpson's rule. Now the focus shifts to adaptive quadrature. So let's see what that holds for us. Adaptive quadrature. Okay, so numerical integration is used to approximate the integral of a function when an exact analytical solution is difficult or impossible to obtain, or impossible to obtain. The whole essence of numerical analysis is the fact that some problems don't have easy solutions. In fact, the solution to some problems are even more difficult than the problems themselves. And that is why it is necessary to have to do numerical approach to some of these problems. So talking about adaptive quadrature is a technique that refines. So that's the idea of adaptation, right? It's a technique that refines the integration process. So it refines the integration process by by dynamically adjusting, by dynamically adjusting the subintervals based on the estimated error. Okay. This approach improves the accuracy, improves the accuracy of the approximation, particularly for functions that exhibit rapid variations or singularities. Okay, so let's look at some key steps. Key steps. Key steps of adaptive quadrature. So we have the initial approximation. Initial approximation. So here, You start by dividing the integration domain into subintervals and compute the integral approximation using the basic method, e.g. Simpson's rule or trapezoidal rule. So you see, just like I said, it's just to help improve any of these other methods. So that's your initial approximation. You start by dividing the integration domain into subintervals and compute the integral approximation using the basic method. So that's the initial approximation. And the second step is the error estimation. Error estimation. So here you estimate the error of the approximation by comparing the results of the coarse and refined calculations. Okay. Then step 3, you talk about the refinement. It is adaptive quadrature and it requires refinement. So refinement, if the error estimate is larger than a predefined tolerance, you split the subinterval further and recompute the integral for each new subinterval. So the idea is, if for instance you did your first estimation, dividing maybe 0 to 2 into 4 subintervals. So if the results you get from that is not good enough, then you can divide into 8 or 12 or something like that. Of course, you're going to take an example to drive home the point. Then you now have the combination at the end of the day. So you have the combination. So after refining the subinterval sufficiently, you combine the results to obtain the final approximation. So let's look at an example involving the Simpson's rule. So example. So when we talk about adaptive quadrature, it can be adaptive Simpson's rule or adaptive trapezoidal rule. So let's look at adaptive Simpson's rule here. Adaptive Simpson's rule. So like I said, it's a method that helps to make the result of any other method you choose, whether trapezoidal or Simpson, better. So imagine the integral. Consider the integral I equals integral from 0 to 1 of e raised to power minus x squared dx. Okay. Because I think that has an easy it has an easy exact solution. So we already know that, of course, s a comma b is equal to, we are talking about Simpsons, right? B minus a divided by 6 into f of a plus 4 into f of a plus b divided by 2. So that's a form of the Simpsons rule that we saw before now. So multiply by f of b. Of course, we can break this down further into even and odd like that, but this is also tenable. So now we start with the interval. We start with the interval 0, 1, so that we now have S01 to be equal to 1 minus 0 divided by 6 of f of 0 plus 4 f of 0 plus 1 divided by 2 plus f of 1. Okay, as two ends. So it means we need to have we need 1 over 6 into f of 0 plus 4f of 0 0.5, 4f of 0 0.5 plus f of 1, like that. Okay, so with this in place now, we can compute the f. We need all the f's, right? We need f of 0, our function f of x. So from the problem we have, right, from here, f of x is obviously f of x is equal to e raised to minus x squared. That is our f of x. So f of 0 would just be e raised to minus 0 squared. That is e raised to minus 0, which is e raised to 0, and that is 1. Okay. Then that's f of 0. Then f of 0 0.5, we have e raised to minus 0 0.5 squared. That is e raised to minus 0 0.25, and that is approximately let me be very sure about this. Let me be very sure about this. The exponent of minus 0.25, the exponent of minus 0.25. Okay, that works. So that's 0.7788, approximately 0.7788. So that goes. And then we have f of 1, which is equal to e raised to power minus 1 squared. That is e raised to power minus 1. And that, of course, is approximately 0.3679. Okay, for confirmation, we have this 0.3679. So that works. All right. So with that in place now, we go on and impute these values. So this is some kind of coarse approximation. So as we continue with this, the coarse approximation, the coarse approximation is now S0, 1 equals 1 over 6 into 1 plus 4. F of 0 is 1. So 1 plus 4 into 0.7788 plus 0.3679. Okay. And so S of 0, 1 is approximately 0.7468. So that's the first thing we can do with this. So we have this result now for the coarse one. Okay. So we can move on again. We go to that. This is we've taken that's step 1 right there, right? So the next thing we want to do is we now want to go ahead and we have done the initial one. So let's see what else we can do. Let's look at the error estimation. So what is the error like in this situation? So the error estimation, to estimate the error, we split the interval into 2 subintervals. So to estimate the error, we split the interval. We are splitting the interval 0, 1 into 2 subintervals. Subintervals. That is 0 to 0.5 and 0.5 to 1, like that. So for the first subinterval, which is for this first subinterval now 0 to 0.5, for the first subinterval 0, 0.5, we have, or we calculate S0, 0.5 equals, because that's 0.5 minus 1, that's 0.5 divided by 6 into f of 0 plus 4 f of 0.25. That's 0 plus 0.5 divided by 2. So that's f of 0.25. Okay. Plus f of 0.5, like this. Then we have s of 0, 0.5, which is approximately, now if you compute all of this, right, you just get 0.47. Okay, let me still go on. Let me still go on. So this is like 5 over 60, if you like, or 0.5 over 6 still. So f of 0 is 1. So we have 4 into f of 0.25 is 0.9394 plus 0.7788. So that s of 0 comma 0.5 is approximately 0.4734. So we have this in place. So the next thing is, so for the next one now, for the second, for the second subinterval, which is 0.5 comma 1, s of 0.5 comma 1 would just be 0, that's 1 minus 0.5, which is still 0.5 divided by 6 into f of 0.5, the beginning, plus 0.5 plus 1, that is 1.5, which is 0.75. So that we have 4 f of 0.75 plus f of 1, f of 1. So with this now we have s of 0.5 comma 1 equals 0.5 divided by 6 into f of 0.4, that's 0.7788 plus 4 into f of 0.75, that's f of, e raised by minus 0.75 squared. So we get something like 0.5703 plus 0.3679. We've seen this before. So s of 0.5 comma 1 is approximately 0.3586. 0.3586. So we have that refinement. We have that happening. So we move on to the next step where we refine the interval. Refining the interval. So, okay, we've talked about the error estimation. So I want to refine the interval. Now, the integral over 0, comma 1 is approximated as the refined s now. So s refined is equal to s 0, comma 0.5 plus s 0.5, comma 1. That's the refinement happening here. And in this case, we now have this to be equal to 0.4734 that we had up there. This 4734 and the one we just got now, this one. So plus 0, plus 0.3586, 0.3586, and that is equal to 0.8320. So in this case now, next thing now, we have to compare the refined results with the initial coarse approximation. So comparing the refined result, with the initial coarse approximation. Okay. We have absolute value of S refined. We have the absolute value of S refined minus S over the whole range. And that is absolute value of 0.8320 minus 0.7468. And that is equal to 0.0852. If depending on our error criteria now, we can, this may still be too big. If our error criteria is like 0.01, this is still bigger. In fact, if it is very small, like 0.000 something, this is still too big. So so we have to keep going. So, but we have to decide on the stopping criteria, right? You have to decide at what point you stop. And we've seen that pattern a lot in previous methods. So let's talk about the stopping criterion. You have to determine the tolerance you want. So when the error between successive refinements is below a specified threshold, it is below a specified threshold, e.g., you may want your threshold to be 10 raised by minus 6. So we stop the refinement process. We stop the refinement process. So this gives us the final result. This gives us the final result. So at last, the adaptive quadrature method improves accuracy by focusing refinement where it is most needed. The adaptive Simpson's rule provides a simple and effective way to compute integrals, especially when dealing with functions that have steep variations or singularities in specific regions. So it's particularly good for some kind of functions. As usual, let's look at what Python has to say about this. So look at the Python implementation for adaptive Simpson Simpson adaptive quadrature or adaptive Simpson quadrature. So again, we're using Simpson's rule. So we define the Simpson's rule there, and then we talk about the adaptation where we break it into parts. So we have part one, part two, and then I mean, you are going to find this code on Facebook. Sadly, we can't get it on Twitter, on YouTube rather. So, but I mean, check on Facebook, just look for my name and you'll find it. So you can easily check the comment and then you can copy the code out and try it out and, play with it and see what happens. So in this case, if we run this now, the estimated value is 0.7468, even at the 8.20. So it means that if we continue iterating, we can, maybe after a number of iterations, we can actually get to this, and you can see the error is pretty small. The error is like 0.50 before you get to 8. And that actually works. So that's how adaptive quadrature looks like. So it just basically helps to refine, to improve either trapezoidal or Simpson's rule like that. So that's how this has been. So if you have subscribed, I should say thank you very much. I say thank you actually. If you have not, please go ahead and subscribe and hit the notification bell so you can always get alerted each time a new video is released. Comment, let me know how helpful these videos are, and let me also know if there's a topic you'd like me to teach or a problem you'd like me to solve. Then like and share so that more people can have access to this great content. Till I come your way again, keep doing math right. Bye.